Gases. Last thing to look at. So properties of gases. We've already talked about these in general, but now you can see them again. Variable shape and volume. They expand and compress uniformly, whereas if you looked at a liquid or solid, they tend to kind of shift on you. Gases, as long as you press down evenly, will expand and compress with that same evenness. Very, very low density, and that's because the space between your individual particles is maximal. We're assuming that there is zero interactions between the individual particles, no intermolecular forces. Okay, so they have to be really far away from each other. If they're really far away from each other, you get a very large volume. A very large volume then means you're going to get a very small density, because how do we calculate density? Mass over volume. If the volume gets bigger, the density has to get smaller, just because of how you calculate that. Another big assumption we make is that when we take different gases and we mix them, they also mix uniformly with each other. Okay? And this again kind of comes back to some of those same principles. We're assuming big, massive expanses of distance between individual gas particles, which then means when we add in a different gas, we're going to still have those same big, massive expanses of distances between particles. The reason we get layers or different phases is because they interact or don't interact. Well, if a gas doesn't interact, we take different gas particles, they're going to mix evenly. There's nothing to prevent them from mixing evenly. Right? The last kind of big difference that comes out with gases is that they can and do exert this weird force on the container that holds them. Okay? Or the container, or exert a force on a container that they are surrounding. Okay? Ideal gases, we've got a couple big assumptions that come out of it. The biggest assumption, which is kind of a bizarre one, is that when we go through and think about our gases and we try to run calculations with them, we assume that the particle of, or the molecule of gas itself occupies no volume. Okay? Anybody think that sounds weird, like that doesn't make sense? Or you're like, oh, that totally makes sense. What are you shaking your head for?
I don't know.
Okay. Let's assume we were gas particles. The first person that came in the room, where do they have to exist? Anywhere. Right? They can be anywhere. The next person comes in the room. Where do they have to exist? Anywhere except for the exact location where that person is. So the instant we put a single particle into a room, what happens to the volume? It decreases. Okay? This means the more particles we have in an individual container, the volume for each of those particles decreases. Okay? Which is difficult to measure because we're looking at changing the volume of very small particles. We have to calculate those particles and all that fun stuff. Except one of our big assumptions when we're looking at gases, okay, is that they have big, massive expanses in between individual particles, which means the density is incredibly low, which then means the instant we put a single particle in, the instant we bring in the next particle, and we want to put it in that exact same space, what happens to the original? It moves. So at any given instant, each of our gas molecules have the entire container to occupy. Okay, so that the overall volume is constant. Okay? Because we're making this assumption, we can go through and develop a neat little conversion factor. That 1 mole of a gas will equal 22.4 liters. For those of you that read extensively Chapter 8 and potentially Chapter 9, this conversion factor is not news to you. Okay? For those of you that did what I asked you to do and not read all of Chapter 8 and Chapter 9, this conversion factor may seem a bit odd. Okay? Because we haven't heard about it before. Have we talked about a mole volume conversion before? Yes, molarity. When was molarity valid? Liquids. Okay. So when we move to a gas, there's an interesting feature that comes out of this. Does it matter what type of gas we have? No. Okay. A single mole of gas will always occupy the same volume. I cannot change the concentration, if you will, of the gas. Okay. there's a massive caveat behind this, which is why I hate introducing it in Chapter 8 and Chapter 9, and why we're leaving it for the very end. For those of you that have worked through the practice exam may have come across a problem that involved this, and we're like, well, how the hell do I solve this without that information? Okay? And admittedly, that is my fault because I haven't talked to you about it. Okay? There's a big reason why I don't include it. When is it valid? Even before STP, because we haven't defined that yet. Gas. Has to be a gas. If it's not a gas, this doesn't work. Okay? If I give you 22.4 liters of iron metal, how many moles are in that? That's a lot of work on the calculator, fair enough. We'd have to go through and convert the volume to mass, the mass to moles, through density conversions and all that fun stuff. Okay? We cannot use this conversion factor because iron metal is a solid, not a gas. But if I somehow heat up that iron solid enough to get it into the gas phase, which you can theoretically do just at incredibly high temperatures, okay? If I take 22.4 liters of that now incredibly hot gas, it would be equal to 1 mole of iron atoms. Okay? So, big first thing has to be a gas. The next big thing is you'll notice it says when at STP. Okay? When it's first introduced, what do they tell you about STP? Exactly nothing. Okay? No context of when this is valid. It is only valid when at STP. Well, what is STP? Not a bad guess, but wrong. Standard, temperature, and pressure. Okay? So standard. Start off with that. What does standard mean to you? Normal. Okay? It's an accepted value. Whatever that value may be, it is accepted, and that's what we work with. Okay? Well, just like with everything else we've done in science, we are all able to get the whole world to agree on one consistent unit or value for all of our measurements, right? So when we go through and measure out mass, we always use grams. We never use anything else, like pounds. Okay, well, that's just an exception. When we look at distances, we always use meters, except for inches, feet. Okay, well, when we look at volumes, we always look at one unit, liters, except for gallons, ounces, cups. Seriously, is there not anything that we can agree on? Pretty true. There's nothing we can agree on. So what the hell does standard mean? Okay. Well, that then applies to the temperature and pressure. What is the accepted temperature? I heard someone already shout out a possible answer. The accepted temperature would be reasonable at room temperature. What is room temperature?
20 degrees Celsius.
Whatever it is, the temperature of the room. Okay, that's fun. What units are you using? Are you using Kelvin? Are you using Celsius? Are you using Fahrenheit? Theoretically, we can convert between those, okay, and come up with a somewhat consistent value depending on how many sig figs we decide to carry through. And we all know how much we love sig figs. Okay? But we could pick a accepted temperature for room temperature. Okay, anybody know the degrees Celsius for room temperature?
25.
25 degrees Celsius is our standard room temperature value. Okay? Is that standard temperature? No. What is standard temperature? Zero degrees Celsius. That is our standard temperature. Why are you questioning that I'm telling you that 0 degrees Celsius is the standard temperature? That is freaking cold.
Isn't that one water?
If we're going to look at the measurement for when a mole of gas equals a particular volume, we have to be at the freezing point of water. How many reactions have you done at 0 degrees Celsius?
0.
Exactly none of them. When is this equation valid in our labs?
Never.
Never. And yet, what are we telling you in Chapter 8? That you have to go through and use it to be able to do your conversions. I find it exceedingly frustrating for that region. go back to the standard aspect of this. Okay, my wife and I were working on some of her equipment, trying to figure out how they'd come up with these calculations, dealing with gases and pressures and all these stupid things. And we spent hours and hours running through these calculations using standard temperature and pressure. Couldn't figure it out. Numbers weren't totaling it up. She finally went into work, talked to somebody, and said, what the hell's going on with this? Thank you, future engineers. Guess what you've decided standard temperature is? 25 degrees Celsius. Which then meant when we go through and look at chemistry standard temperature of 0 degrees Celsius, numbers don't match. So if somebody tells you STP, don't take them at their word for it, because what they're using as STP is not necessarily STP. Okay? It is whatever they have deemed the standard to be. Okay? So you need to ask. When it comes to this class, your standard temperature is 0 degrees Celsius. Also known as Kelvin? 273. Okay? Which would be well within roundings. You'd probably be okay. Pressure. Okay? Pressure is this magical force that's then contributing to this. What is the standard pressure going to be? Okay, 0. Okay, what does it mean to have 0 pressure?
Nothing's happening.
There is nothing pushing. If you have a gas, what is the gas doing? Pushing. So as soon as we have a pushing force, our pressure can't be 0. So pressure is not going to be 0.
Got it.
Right? Our standard pressure will be the pressure exerted by our atmosphere at sea level. Okay? And we'll talk about pressure and its freaking messy, nasty units in just a little bit here. Okay? What is going to be a problem with that observation? The pressure at sea level.
We're not at sea level.
We're not at sea level. There's plenty of places on the planet we are above sea level. What happens to the pressure? It changes and it gets
Less.
lower. Pressure gets reduced. There are places where we're below sea pressure or sea level, in which case it increases. We get larger pressures. Okay? So we are telling you this is a magical conversion factor that allows us to convert moles to liters, but it's only valid when it's a gas, at standard, which is arbitrary, a temperature, which we never work at, and a pressure at which we no longer exist. That sounds like a really useful thing to memorize. It is not valid ever. Useful.
Agreed.
Okay? That said, it's on your final. Okay? You are required for knowing this conversion when it comes to a gas. If you have to move into 151, you'll look at the full-on expanses of where that is coming from, and depending on our time, we might actually derive that conversion factor. But it's looking at all of the features that combine to give us some information about gases. Pressure is one of those, volume is one of those, temperature is one of those, and the amount of gas particles is the last one. So there's 4 different variables that we can use to control and predict our volumes. If we hold some of those constants, we can end up with a nice conversion factor, and we can use that conversion factor to solve questions. Okay? Do not confuse this conversion factor with molarity. They are identical units, except this one works for gases and molarity works for solutions, officially. Liquids assumes a pure species. We're looking at a solution, a mixture. Okay? You don't have to be happy with it, but you do have to use it. Gases, yeah, that one. Low density, uniformly. This is where we bring in our homogeneous mixtures. Remember those definitions way back when in that first unit we talked about homogeneous and heterogeneous? Okay. Our gases will always give us a homogeneous mixture. So if you ever asked a question, which of these is homogeneous, and they say air, that's a homogeneous mixture. Okay. Questions about that? I didn't think there'd be a question there. We didn't give you any questions to ask. So our force of our gas particles is what we've deemed our pressure. So before we get into pressure, let's go ahead and use this molar volume thing, which is irritating, but we're going to deal with it anyway. How many liters are needed to hold 2.0 grams of hydrogen gas at standard temperature and pressure? Note the big hint here. It says standard temperature and pressure. Okay. Anytime that you're going to be using that 22.4 conversion, you should be seeing standard temperature and pressure listed. If it's not listed, it could very well be just as simple as a typo, or there could be some sneak trick question associated with it. Okay. So, setting this up, where do we start? We want to know what we're trying to get to. We're trying to get to liters. Liters of hydrogen gas. We need our complete unit. So the measurement liters and the substance H2. Okay, what are we starting with? .0 grams of hydrogen gas. Ideally, we'd say what we have on the left equals what we have on the right. Is that true? No. So we're going to have to do a conversion. In our ideal conversion, we would have our liters of H2 on top and half right, grams of H2 on the bottom. So that our gram units cancel and our liters then come out as our final answer. Okay, we'd be comparing the mass to the volume for hydrogen gas, also known as the density. The density for hydrogen gas. Are we given the density of hydrogen gas? No. So this conversion factor, while our ideal situation, we don't have that conversion factor. Okay. Do we have a conversion factor that could convert grams into anything else? We could go grams to moles. Okay. Is that going to be a valid way to go? I don't know. Let's find out. Okay. Where do I find the conversion factor between grams and moles? We go to the periodic table. Pointing is nice. We look up hydrogen. Hydrogen has a mass of 1.01 grams per mole. However, there are 2 hydrogens, so I need to multiply by 2, and I get a mass of 2.01 grams per mole. Where does the 2.01 show up?
Why isn't it 0.02?
As soon as I said it, I was like, I hope no one answers. 2.02, then I was going to subtly fix it, and we substituted it in. Okay, 2.02. Where does the 2.02 show up? No. No. In front of grams.
Oh, come on.
I don't care what you mean. Say what you mean. Okay, 2.02 shows up in front of the grams of hydrogen. What shows up in front of moles? 1. What unit do we now have? We have moles of H2. Is moles of H2 our final answer?
No.
No? So what do we have to do? Ideally, I would get moles of H2 converted into liters of H2. Do I have a conversion factor between those? Yes. What is that conversion factor? 22.4 needs to show up where? With the liters. What shows up in front of moles? 1. I now have the ability to punch it into the calculator, and I should get my final answer. Make sense? Questions about that? Okay. Same general method as we've been doing for every other type of question, except now we have an extra conversion factor. We can convert between moles and liters using this ideal gas expression. Okay? I don't remember. Do I give you another one? Oh, there we go. More practice. How many liters of hydrogen are produced from the reaction of oh, this is kind of mean, but you can do it. 0.165 grams of aluminum metal with dilute hydrochloric acid. Okay. Where are we on quizzes? Should we do this as a quiz? Why not? Actually, no, I lied. I don't have any papers. I can't do it as a quiz. But I will have you guys work through it on your own. I'll set you up. Where do we want to start?
Liters.
Half right. Liters of hydrogen. Okay, officially our hydrogen gas, so H2. What are we starting with? Ideally, we'd go grams of aluminum to liters of hydrogen gas. That conversion doesn't exist. So I need to convert the grams of aluminum to something else. Okay. And I will also, so not only do I need to convert the measurement, grams, into something else, but I'm also going to need to convert the substance. How do we convert substances?
Balanced equation.
Through the balanced equation. Okay. Go ahead and start working. Go ahead and pick this one up. So as was just pointed out, whoever wrote this question did an awful job at it. Might have been me. Did not include a very useful piece of information. That useful piece of information would be standard temperature and pressure. Because if we're not at standard temperature and pressure, our answer goes a little haywire. It becomes a little bit more difficult to solve. So it has to be at STP. Okay? And we'll readdress why, when and why that STP becomes relevant when it shows up. So grams of aluminum, we cannot directly convert into liters of hydrogen. So we need to convert our grams of aluminum into something. What can I convert grams of aluminum to? Moles. Okay. If you remember way back when we first started talking about dealing with conversions, the very first thing I told you to try and convert to was moles. Hey, look at that. Another question. We're directly converting into moles. Moles are a very powerful unit. Get it into moles, and you've got most of your problem solved. How do we convert between grams and moles? From the periodic table. So what we need to do is take the formula in our question here, and our formula for aluminum is? Formula for aluminum? Al. Okay. A lot of people wanted to bring in a 2. Okay, so we want to be a little bit careful with that. Okay, you're bringing in the 2 from the balanced equation. Okay, so number 1, have I balanced the equation yet?
No.
Why not? Am I at a point yet where I need to use it?
No.
No, that's why I haven't balanced it. Okay, so we'll come back and balance it in just a second to see what that 2 is doing. The 2 is necessary to balance the equation. It is not necessary to balance the formula for aluminum. Meaning, what is the formula for aluminum? Al. That's it. Not 2Al or Al2. It's just Al. Okay? Which means when we go to our periodic table, we can just pull the number straight off, which, as Jacob keeps telling me, was what, 28.93?
26.98, man.
26.98 grams of aluminum. For those of you who want to skip and round, 26 is a dicey round.
27.
You said 27?
Yeah.
Good. 27, probably can get away with 27 for rounding for the sake of your calculations. Okay, and I'm going to temporarily cover up our microphone here. The only reason you can get away with that type of rounding is because when we look at sig figs in our calculations, very rarely on a multiple choice test will we provide a whole bunch of rounding type answers. You'll get one answer, okay, and your answer, depending on how you've rounded out your calculation, may be slightly off. Okay. If it is a test written by me, you have to be a little bit careful because all the other answer choices were all very intelligently or brutally, was it brutal? Is that the word?
Calculated brutality.
Calculated brutality in the design of those answer choices. When it comes to how most instructors write answer choices, they come up with one that's correct, and they say, well, I don't want to deal with calculations. And they just make up a bunch of other numbers. Okay? So if you just randomly punch buttons into your calculator and you find something that comes out, unfortunately, you were probably right and you got randomly lucky. Okay? Doesn't work on any test I write, but it does work very frequently on tests written by other people. Like maybe, oh, I don't know, the final. Okay?
Be surprised.
So, 26.98 grams aluminum per 1 mole. We're now in moles of aluminum. I want liters of hydrogen. Ideally, I could drop in my conversion, moles of aluminum, and hopefully get to liters of hydrogen. Okay. That conversion factor does not work. Okay. We are changing a substance. We have to get our substance converted before we can change units or measurement values. Okay. So how do we convert our substance, moles of aluminum, to say moles of something relevant? What's our something relevant? What's the something relevant I want to convert those moles to? Hydrogen gas. Can I convert it to HCl?
No.
I can. That is perfectly valid to go through and do it. Does that get me closer to what I want as an answer? No. So be selective in what you're trying to convert. Okay, so we want moles of hydrogen in our conversion. Where do we find that? Our balanced equation. So we can go up and go through and balance. Aluminum, 1 and 1. Chlorine. I would recommend saving the hydrogen for last. And again, when we talked about balancing equations, said to leave hydrogen and oxygen typically for last because they are trickier to balance. Okay? You can still balance the equation if you start with them. It just makes it more difficult. Stop shaking your head, Sam. I'm doing it right.
Oh, I'm just,
It's okay.
no, I'm not.
Chlorine. 1 on the left. How many on the right? 3. Is it balanced? What do I need to do? Now my chlorine is balanced. So I'll move down to my hydrogen. How many hydrogens do I have on the left?
3.
On the right? 2. How do I make them balance? Okay. I need a common way to multiply between these. We did the same kind of thing when we balanced out our combustion reaction with oxygen. Remember that one? Because, oh, this is horrible. I never want to do this again. Here it is. Got to do it for this one. Okay. We need to make sure that we have a common multiplier between these. We can do that by making it 6 on both sides. To make it 6, what did I do? I multiplied everything through by 2. Check the work. Aluminum, how many do I have on the left?
2.
On the right?
2.
Chlorine? And hydrogen? And 6. What do we do now?
Plug it into your...
Check it again. Thank you. Okay. Now that you're irritated at me for asking that, we'll go through and move on to the next step. Okay. Now that we have our balanced equation, we can bring in that factor of 2. Okay. Why do we have a 2 in front of the aluminum?
Because that's our coefficient.
I need 2 aluminums to react with 6 HCl. That's why there's a 2. If we go back and look at the conversion factor between moles of aluminum and grams of aluminum, is HCl in that conversion? No. Why was the 2 up in the equation? 2 aluminum to react with HCl. Okay. They're showing up for different reasons. Okay. I cannot bring that 2 into my conversion factor for the molar mass. That said, where do I now put in the conversion factors? 2 moles of aluminum, 3 moles of hydrogen. Okay. And officially gas, yes. What would our unit now be? Moles of hydrogen. Is that our final answer? What do we want? Liters of hydrogen gas. Yep. Good catch. Just testing you. Let's make sure I don't do it again. Moles of hydrogen. Liters of hydrogen. What is our conversion factor? 22.4 liters is 1 mole. We can then put it into our calculator and we have our final answer. Fun stuff. Questions about any of that? Fairly confident? Easy? Ish? Okay, we'll accept ish. So, back to our pressure. Our gas pressure is a result of our gas constantly moving around. So when we looked at our kinetic energy theory, our gas particles had the highest kinetic energy because they're constantly moving. Well, if something is constantly moving, it then constantly encounters something else, and we get collisions. Our pressure is a measure of those collisions, okay, and the force at which the collision is happening. Right? If we think about pressure in general, okay, is there a gas pressure currently being exerted?
Yeah,
Yes. How do we know that?
because it's all around us going up, and as it goes down, it gets bigger.
We have shape. What happens if we remove all of our pressure?
We lose our shape.
Well, you just take us out into space. No spacesuit, we just say, whoop, here you are in space, now what happens? We die rather painfully because there's now nothing holding us together and everything kind of explodes apart. Not the nicest feature. Okay? So, pressure is being exerted. There is something that we would call our natural pressure or our atmospheric pressure. Okay? It's just what we naturally have around us. This was observed because you can take a rod, fill it with liquid, and put it in another pool of liquid, and then when you invert it, you'll notice that the liquid inside the rod won't just drain completely out. It stays in there a little bit. Why would it stay in there? Something has to be pushing up against it because gravity is pushing down on it. So something is pushing up. What is that something pushing up?
The atmosphere.
It's our atmosphere, which is a little bit weird because when we look at this tube, where's the arrow for our atmosphere pushing? Down. And yet what I'm saying is that atmosphere is actually pushing the liquid up. How is it pushing the liquid up? It's pushing down on the liquid on the outside,
The water needs somewhere to go.
and then that liquid is then pushing up on our center column to keep the liquid inside the column. Like a teeter-totter, since you keep suggesting that. Okay. What happens is our atmospheric pressure on the outside is reduced.
Well, liquid goes.
The liquid starts to drop lower because there's less force pushing up on it from our atmospheric pressure. Okay. So we can monitor or see that when we move to different locations, our pressure changes. We could use this to interpret weather patterns because as the concentration of water in our atmosphere changes, we also change the pressure. That pressure we can correlate or tie back to tie back to weather patterns involving rain, snow, all that fun stuff. Okay? So how do we go through and measure that? Well, if this was our first observation, how did we measure it? Took our tube and we said, well, how high is the mercury? Or how high is the liquid inside that tube? Okay? By measuring the height of that tube or the liquid within the tube, we now say this is a standard pressure. Okay? That's it. That's all our pressure is. Okay? As we increase or decrease it, that height changes, and we match that back to a change in our standard pressure. Okay? One of the problems with measuring our pressure this way is what happens if we use different liquids. Are we going to get different heights within the tube? Yes. So we have to be consistent with the type of liquid we use. Okay? So that's fine. Let's say we're just consistent. Are there other features that could become problematic? For instance, you'll notice that what is it sort of listed up there? Mercury. Why are we not using water?
Water evaporates.
What's the issue with water evaporating?
There's less water.
There's less water in there. If there's less water, what happens?
Like the atmosphere is
It's going to start to look like our pressure is dropping because there's now less water to push up. Okay? So what we need is a liquid that does not evaporate. Okay? Well, because this is a pretty standard issue, we want to now define this term, this issue with water evaporating. Okay? So water evaporates a lot. Mercury doesn't. I want a fancier term. It's water, or it's our liquid turning into a vapor. By turning into a vapor, what does it do to the atmosphere? We're taking more particles and putting them into vapor state. We have more gas. What is that going to do to our pressure? Should increase. So what we're looking at is evaporation, the generation of a vapor that now affects my pressure. So I have a vapor pressure. Okay. So what we are looking at is just a vapor pressure. What is going to determine our vapor pressure? Okay, let's take a look at water versus mercury. Which of those two would we expect to have the greater vapor pressure? Okay, what is vapor pressure?
Higher pressure, low boiling point.
It is a higher pressure, and our pressure is measured by, where do we see pressures? What section was this? Very first slide started with
Gas.
gases. It is the pressure of gases. So it is a higher gas. When would we have a higher gas pressure? Okay. Well, for determining our atmospheric pressure, what did we want? Do we want it evaporating? No. Okay, that needs to stay constant, which means we would expect the vapor pressure, the pressure at which it is a gas, to be very small or very large?
Very large.
Okay, if I have a very large vapor pressure, what does that mean?
What? I mean, well,
You have a higher gas.
You have a higher gas. What did we say we wanted for the liquid? We want it to stay a liquid, not a gas. We want an incredibly low vapor pressure, okay, as our standard solvent. So water has a much higher vapor pressure than mercury. Okay. Whatever liquid we're using to observe our pressure, we want to stay a liquid. The instant it starts turning into a gas, that's now going to start to affect our pressure readings. So it has to stay liquid, so it doesn't interfere with what we're observing, the gas state. Mercury is a great liquid to use because its vapor pressure is incredibly small, meaning it does not turn into a gas. How can we potentially derive this or look at what we already know to predict something about our vapor pressures? The vapor pressure is a measure of how much of it becomes a gas. Okay. Is there something else that measures, say, how we move from a liquid to a gas? Boiling points. Okay. If we're looking at our vapor pressure, if we want a low vapor pressure, what does that tell us about our boiling point? Why would the boiling point need to be high? I mean, vapor pressure is low. What is our boiling point a measure of?
When a liquid turns into a
The
gas.
energy to turn it into a gas. If I want a low vapor pressure, what would I expect the boiling point to be? Very, very, very high. Meaning the point at which I transition from a liquid to a gas, i.e. the vapor, needs to be very, very high. Okay, they are inversely related to each other. Sort of with me? Okay. Is there something that we've talked about where we could look at a compound and predict something about its boiling point? Our intermolecular forces. So if we have a vapor pressure that is low, that's going to mean a higher boiling point, which then means stronger intermolecular forces, or IMF. What does that mean, about the bonds? What type of bond would I expect?
Ionic.
Okay, I would expect a more polar bond. And as Jacob just suggested, our most polar bond is ionic. So if you see a question about vapor pressure, okay, I personally like that kind of question, and you will see it on the final, and it is on the practice exam. Okay? It is getting you to tie together multiple different ideas and concepts and asking you to manipulate and think about them. What is our vapor pressure? Can we predict vapor pressure based on boiling point? How do we predict boiling point? Stronger intermolecular forces. How do we predict stronger intermolecular forces? We need more polar bonds. Okay? So I could ask a question about vapor pressure and just give a bunch of structures. Okay? Because you need to be able to tie those two thoughts back to each other. Much the same way that you're tying your conversions back to each other. Okay? Kind of makes sense? Okay. So there's our vapor pressure concept. Okay? When we look at mercury as our choice, it's because it doesn't turn into the gas phase, which means I see less evaporation, which gives me a better system to evaluate. Okay? We can also use vapor pressure outside of just our general gas laws and looking at dissolving gases in liquids. And we already talked about dissolving gases in liquids, right? Say yes. Okay, shaking your head up and down works. Okay, what did we look at to dissolve a gas in a liquid? What did I try to do? To get a gas into a liquid, what's the easiest thing I should try and do? To convert a gas to a liquid, what do I want?
Cool it down.
Cool it down. Drop the temperature. Why? What happens when you drop the temperature?
Closer to the.
You get compounds start moving less and they start equating to a liquid. So if I'm trying to dissolve a gas into a liquid, I want to drop the temperature because I can then slow those gas particles down and drive them into the liquid phase. What's the other thing I want to do? Okay. I'm taking this big gas and I now want to get it into this tiny little container. If I cool everything down, that's going to get the particles moving less and potentially get them to drive into the liquid phase. What else do I want to do? I want to force them all into one space. Okay. As I shrink the volume down, what ends up happening? The pressure increases. Okay. So to get my gases to dissolve into a liquid, okay, I want to decrease the temperature, I want to decrease the volume, and I want to increase the pressure. Think back to your soda cans. Okay, you left the soda can in the car, probably even right now might be a problem. What's going to be the issue? I guess you've had experience with this.
The second month I got my car,
Yeah.
all of this, it's still staying.
Nice. What happens? It explodes. Why does it explode? What's happening in the car?
Pressure
Okay. Heat. The heat comes in and takes the gas that's dissolved into the liquid phase and makes it do what? Turn into a gas. Okay. Eventually, what ends up happening? It builds up enough pressure that the canister that we've designed to contain that pressure, our aluminum can, eventually decides it's had enough and explodes. And we end up getting the soda sprayed all over the car. If you want to reverse that process, drop the temperature and increase the pressure to force it back in. Okay, just as simple as that, and you could have cleaned up the whole mess.
How come it's like
Only
when you
took this class.
freeze the soda can in the freezer?
So there's an interesting question. What happens when you freeze a soda? It expands. But isn't that cooling it down? Why is it still exploding?
Is it mostly water?
Oh, okay.
It has to do with water. Liquid water, when it freezes, actually expands its volume. So it's a different process. It's actually not the CO2 causing it to blow up, it's the water causing it to break the seals. So, this is chemistry. Physicists just want to co-opt it. Okay. Units of our pressure. Tons of different units of pressure. Kind of sucks. We typically stick with atmospheres. 1 atmosphere is our standard measurement. Okay. Typically it's measured off of mercury. You'll sometimes see inches of mercury show up because we're American. I don't know why we don't pull the American card and stick with atmospheres, but you'll see inches of mercury. After that, you'll see centimeters of mercury because, of course, there's different ways to measure distances. Millimeters, of course, Torr?
Yeah.
Yeah, what? Good question. Pounds per square inch? That's like so American, we're American Americans. Like that's just, I mean, you're just screwing everything up to come up with that unit. I mean, really, you're taking mass and you're using the American unit. You're taking distance and you're taking the American unit. And then you smash those all together to make like a robotic, awesome American unit. There's our PSI.
It's like Power Rangers.
Okay. Kilopascals. Okay, again, where are these units coming from? Pressure is such a big, obvious-ish kind of observation that multiple people around the world made these individual discoveries. What happened when all those people got together and said, hey, your result's the same as my result? I'm bigger than you, you're going to call it my measurement. No, I'm bigger than you, you're going to call it my measurement. And they fought until no one agreed, and we end up having to deal with all the different units. Okay? So we end up having to deal with tons of different units. Depending on what system you're working with, different units hold different meanings and different utilities. Okay? And that again comes from who's using it. For instance, if you try to inflate your car, we don't measure it in atmospheres or inches of mercury. What do? PSI, because we're looking at the pressure within the wheel pushing outwards on the wheel. Pounds per square inch, because we're looking at how it affects the wheel dynamics. Okay? Depending on what you're working with, you have different units. Guess what you get to be responsible for in 151? All the conversions. Yay! Guess what you're responsible for now? None of it. Yay! 1 atmosphere. Okay? That's what you're responsible for when it comes to pressure. If you're going to work questions from the textbook, they will have you interconvert between all of those. You just kind of have to deal with it. Okay? Back to our ideal gas behavior. Okay? No volume is huge. The instant our particles hold volume, that expression, mole of gas equals 22.4 liters, is invalid. Okay? That turns life really crappy really fast. Okay? We assume random directions and no attraction for one another. Okay? Anytime our particles collide, what happens to them? They freely bounce in what is known as an elastic collision. Okay? You get pool cues bouncing across the table. Okay? Imagine playing pool where you hit the pool cue and then it sticks to the ball. Okay, that you're trying to hit, or the cue sticks to the cue ball. Okay, that becomes a bit of a problem. Okay? So we are assuming an ideal gas situation. Okay? If we make these assumptions, we end up introducing some variables that can affect this. Okay? In particular, the variables that can affect our pressure. How could we change the pressure? We could shrink the space. If I take a balloon, right, it's filled with a certain pressure of gas. How can I increase the pressure? I take the balloon and just compress it downwards. What happened to the space within that balloon? Became smaller. What did I just change? The volume. So there's a relationship between pressure and volume. What is that relationship?
More pressure to less volume.
There it is. As I increase pressure, I decrease volume. Mathematically, this comes out as saying pressure is proportional to 1 over the volume. As volume gets smaller, what happens to pressure? Gets bigger. Okay? And that's what that alpha sign is referencing. It's a proportionality. Okay? Similar to equals, but not the same. Okay? It's not the same because there's something else that can contribute to pressure. What else can I relate pressure to? Temperature. I take that balloon and I start to heat it up. What happens? It expands. Okay. Sorry, that brings in volume. Let's avoid bringing in volume for the moment. I take that balloon and I make sure I can't change its size. What happens as I heat it up? The pressure starts to increase. It wants to expand, right? Okay, but if I'm keeping it contained as that same volume, it just starts to try to expand until eventually it probably blows up in my hands. Okay, so what happens between pressure. If I increase my temperature, what happens to the pressure? Okay, which means, which means what?
Pressure is alpha temperature.
Our pressure is directly related to temperature. Okay, or proportional. One last comparison. I take that balloon, make sure I can't change its volume, so it's got a certain pressure associated with it, and I blow more air into it. What happens to the pressure? It increases. By breathing more air into it, what have I changed? The number of molecules. The number of molecules we use as what unit? Lots of different units getting tossed out there. Moles. Moles is our number of particles. Okay? Mass is a measurement of the number of particles, the mass of those particles. Molarity is a relationship between the number of particles in a given solution. Okay, so it's our moles. This gets fun because when we look at pressure, what unit do we use, or what symbol? Capital P, because pressure begins with P. Volume? V. Temperature? T. Moles?
Moles for moles.
Okay, I want a single letter unit for this. What's the issue if I use M? It's potentially molarity or mass. Okay, depending on whether I use capital or lowercase. Okay, we could always go into the Greek alphabet because we love doing that, or using italics because that's always easy to see when we handwrite. So instead, what do we end up using? N. N is our symbol for moles. Okay. What happens when we increase the number of moles? The pressure increases, which means when we look at our relationship, N is directly proportional, trying to be consistent. N is directly proportional to the number of moles. And we've got that system. What we just observed took something like 400 or 500 years of a couple other scientists coming up with these. Okay? So great. In 5 minutes, we just discovered something that now students are responsible for attaching a name to, and we have Charles' law. Oh, it's all right. Didn't mean to offend you. Charles' law. We have Avogadro's law. We have Boyle's law. Okay, what did they do? They took the variables that affect pressure and they found relationships between them. Those same relationships we just talked about. Okay? I think that's a bunch of nonsense. People rubber stamping their name across a stupidly obvious observation is annoying. Okay? That said, depending on the class you move into, you may end up seeing people ask you to have these relationships memorized according to their names. Okay? For the sake of this class, you don't need to stress on it. Okay? What it ultimately comes down to is someone then compiled all of these and said, hey, all of these things are related to each other, and if we plot them, we can see this kind of constant relationship. So I'm going to take all of those and smash them all together. And I'm going to smash them all together to make this relationship. I found that if I plot pressure times volume and divide that by the moles times temperature, regardless of the system, I always end up with this R. Well, that's cool. I put a bunch of numbers in and a letter pops out. That was a joke.
I just refuse to laugh.
Okay, I appreciate that. Okay. R is a constant. It is known as the gas constant because it's a gas. Okay. So if we put all these things in, we find that all of these terms come together to give us a single constant value. That constant value is 0.0821 atmospheres times liters divided by moles times Kelvin. Interesting observations in that. Within the temperature, what unit are we using for temperature? Kelvin. Okay, why did we use Kelvin and not degrees Celsius or Fahrenheit? for the sign. Degrees Celsius and Kelvin both have negative values. If we put a negative value in, we're not going to get the proper conversion value here, or that number. So that's why we stick with Kelvin, because our Kelvin values will always be positive. Moles, fairly self-explanatory. Liters, also fairly self-explanatory. Notice the atmospheres. That is our standard unit for pressure. That is the one we will maintain and continue to use for everything. Okay? Why is this useful? I can take that simple expression and I can rearrange it. I can rearrange it to say I want to know the pressure for a given system. Okay? To solve for the pressure, I take my moles and I multiply by the gas constant, by temperature, and I divide by volume. So if I know 3 of 4 variables, I can figure out the 4th. Okay? And I can rearrange that any way I want. This equation becomes so popular that I had a science teacher back in high school insist, at least allegedly claim, that she had a license plate made with PVNRT and then put an equal sign in it so she could run around and say that was her license plate because it was so important. Okay. Why would you pay at all for a license plate? I mean, really? Okay. She also then claimed that a cop pulled her over because she modified the license plate by putting in an equal sign. Okay. I'm not sure I believe any of it.
You ever look at a car?
No. Pivnert. Okay? So if you hear people refer to Pivnert, this is what they're referring to. PV equals nRT. That equation solves every system that you could ever ask for in gas laws. Okay? What happens at standard temperature and pressure? Well, standard temperature was 273 Kelvin. Standard pressure, 1 atmosphere. If I rearrange this equation, I can get volume. Actually, I'm going to do it the other way. I can say that moles equal RT over PV. If I take my R, 0.0, is there another 0 in there?
No.
Okay. Liters, atmospheres per mole Kelvin times my temperature of 273 Kelvin. Divide that by my pressure of 1 atmosphere. And I put my volume in here. Yeah, what did I do? Oh, that's what I did. God, freaking algebra. Or do it better that time? Yeah, there it is. Now I gotta write all those same freaking numbers. 1 atmosphere, our volume, 0.0821 liters times atmospheres. What happens when I go through and punch this all into the calculator?
Give me the number.
Yeah, any ideas what that number is? You get 1 mole is equal to 22.4 liters.
Whoa.
At least I didn't throw it that hard. Almost took someone's head off in organics. Okay. PV equals nRT. When does it work? All the time, as long as you're an ideal gas. When does this 1 mole 22.4 liters? Ideal gas at standard temperature, at standard pressure. Okay? For the sake of this class, mole equals 22.4 liters is all you really need. For 151, you will go through a half dozen different variations of PV equals nRT. They're all doing the same thing, and they will try to tell you that it is something different. It is PV equals nRT every single time. Okay? So, tons of different conditions we can go through and do. If we have conditions at set A and we change those conditions, okay, we would get conditions at set B. The gas constant will always hold true, which then means pressure times volume divided by moles times temperature for condition A has to be equal to
Condition B.
pressure times volume divided by moles times temperature for condition B. They will always come out the same. Okay? So we could go through and do a whole bunch of nasty fun calculations. I'll leave you to be excited about that later if you really decide you want to do so. If we went through to do some of the more simple calculations, how many moles of neon gas occupy 2.34 liters? Notice the at STP is there because we're trying to make it easy. You guys seem awfully excited about solving this. Moles of neon. How do we convert our liters of neon to moles of neon?
Isn't it two? Because it's gas or no?
What's that?
At any two or no?
At what?
Is any like two or no?
It's the formula for neon.
Any two?
Oh, sorry.
Is it?
Totally not on the right page.
No, it's not that.
Neon is not a diatomic element. Okay. Your diatomics are fluorine, nitrogen, oxygen, chlorine, bromine, iodine, hydrogen. I'm going to say it was chlorine. Have no fear of ice cold beer.
Or Knopfklubler.
What do you say? What do you say?
Knopfklubler.
That's awesome. That's absolutely awesome.
Is it?
I think I'm broken. Go through and solve, and we'd end up with our final answer. Okay. You can go through, set that all up. We could do a whole bunch of other conversions. There's Dalton's law of partial pressure. I know, we're almost done here. Dalton's law of partial pressure means take each of the individual partial pressures, add them together, and what do you get? The total partial pressure. Why? Because our gas particles don't interact with each other, which means they have an additive property to get to the total pressure. Relatively simple. You just add them up and you end up with your answer. I promise this is the last thing I wanted to say. Absolute zero. This is where degrees Kelvin comes in. Okay. According to Pivner, all motion stops at 0 degrees Kelvin. Okay. Because at that instant that we cross through 0 degrees Kelvin, what happens? Pressure, volume, or moles need to become negative to counteract the negative temperature. Okay? That's kind of a bizarre mind blow thing. If you want to talk about that later, we can.